I started off by first graphing the acceleration and force values with respect to time. When comparing these two graphs, I noticed a common trend that the acceleration started from rest and reached a constant acceleration before hitting the stopper, while the force stays almost constant throughout that time. So I then zoomed in on a time where the acceleration was as close to constant as possible. Therefore, only tension was acting on the cart during this time. Using these two tabulated values, I solved for an average constant acceleration and an average force. I've done all the calculation. Using these two tabulated values, I solved for an average constant acceleration and an average force. I've done all the calculations using unrounded values, but rounded on the diagrams throughout this presentation for simplicity. I then drew some free body diagrams, assuming that friction has a negligible effect. Using these free body diagrams, I solved for the combined mass of the cart and the bumper. I first calculated the tension, and then used that tension force to calculate the combined mass. I then drew a free body diagram of the cart. Using this free body diagram, I could solve for the mass of the cart, and thus the mass of the bumper. Finally, I drew one last free body diagram. I then solved for the acceleration relative to the mass and realized that this value is what I initially started with. Using this calculated acceleration, I calculated velocity and position relative to time, assuming constant acceleration, and then graphed everything. The position and velocity gradients looked the same, but the acceleration gradient was different. This is because the calculated acceleration assumed that tension was the only force acting on the cart. Thus, we have a constant acceleration, while in reality there is an unknown force, possibly friction, opposing motion at the start, and as the cart nears the magnetic field, the magnetic bumper and magnetic stopper begin to interact with each other, which creates another force that opposes motion, hence the slight decline in acceleration towards the end.
Hi guys, this is our second home experiment for dynamics, and in this experiment we will use and explain the coefficient of kinetic friction. We have found the researched value of coefficient of kinetic friction to be 0.3 between wood and wood. In this scenario, we will be dropping the honey can on the right down, and we will use a fixed length of rope that doesn't extend or shrink through to the phone, and the phone is connected to the block, so the length is fixed. When we drop the can of honey, it will accelerate the phone, and we will record the acceleration using the app called Science Journey, and we will try and work out the coefficient of kinetic friction.
I will use the honey can to be the honey mass, and it has a mass of 220 grams. And the total mass of my phone and this wooden block is 237 grams. According to the research, the kinetic friction coefficient of wood on wood is 0.3. And let's see if that applies in real life condition. I will use this kitchen board and the wooden block to generate kinetic friction force, so we can calculate the friction coefficient. After this, I will make this surface inclined and double check. So I will drop the honey mass, which is a honey can, and measure the y acceleration of the wooden block using the app called Science Journey.
We have repeated this experiment 10 times, and the results from the acceleration has been recorded as shown here. Through the use of those 10 experiments, we have been able to calculate the acceleration to be about an average of 3.2 meter per second square. We calculated the tension force in the rope to be 1.45 newtons. We used the weigh scale as shown in the video before to measure weight force, and then used the tension force as a reference. And then by using the principles of kinetic friction, we have been able to work out the friction to be 0.3. Calculated value of friction coefficient is 0.297, pretty much similar to the research value of 0.3. Now we will use this as a reference point to work out the coefficient of friction on an inclined plane. In this part of the experiment, we will be using the same kitchen table and the block that we used in the last experiment, and the same honey tub to generate the acceleration as a hanging mass. In this part of the experiment, we are trying to figure out the angle theta and use the app called Science Journey to record it. And through this experiment, we will be trying to work out the angle, which will help us to work out the coefficient of friction. By the use of Science Journey app, we will be recording the average acceleration of the phone, because the length of the rope is fixed, and we can measure the weight of the phone and the tub, and we can assume that the weight of the rope is negligible for this case. Also, we will be adjusting the angle of the table as shown in the video. As shown here, you can see the values of the results of acceleration on an inclined plane, and for this experiment we will take the flat surface of the graph to calculate the average acceleration. For the first one, we will be using the acceleration of 2.45 to calculate the average across the 10 of them. Now we were calculating the average acceleration, which came out to be 2.6 meter per second square. As you can see in the free body diagram, we work out the tension force. Now we use the rotated coordinate system to work out the angle theta in this case. Calculating the formula for the normal force, we can also work out the formula to work out the coefficient of friction in this case. As you can see, the approximately angle is around 7 to 8 degrees for the inclined plane. As you can see now, we are trying to measure the angle of the inclined plane that we used. As in this app shows, the angle is approximately 8 degrees. As you can see, the researched value of coefficient of friction of 0.3 is also valid for inclined plane as well as the horizontal planes. Thank you and have a good day.